Welcome to MathAlgo Studio, where math meets code. This is the very first lecture of our computational geometry series, designed to take you from beginner to advanced in a structured and practical way. In this lecture, we begin with the fundamental building blocks of geometry, points and lines in 2D and 3D. Understanding points and lines is essential because almost every geometric concept, planes, triangles, polygons, meshes, or even advanced algorithms like convex hulls and Voronoi diagrams starts from these basics. So today, we will set a strong foundation that will help you throughout this entire series. In this lecture, we are going to cover 5 important concepts. What is a point and what is a line? We'll understand the mathematical definition and how computers represent them. Types of lines and their segments, including collinear, parallel, perpendicular, and the difference between lines, rays, and line segments. How to find the slope of a line, one of the most important properties in 2D geometry, used in intersection and angle calculations. 3D line equation and visualization. We extend the idea of lines into 3D space and understand vector form and parametric form. C++ code to calculate the equation of a line. Because this is a computational geometry series, we'll also implement all concepts in C++. Finally, we will go through examples with complete solutions, and at the end, I will give you practice questions to test your understanding. Let's begin building your strong foundation in geometry and C++ together. Let's start with the most fundamental concept in geometry, the point. In geometry, a point represents an exact location in space. It has no size, which means it has no length, no width, and no depth. It only represents position. Point in 2 dimension required only to coordinates x and y. Let's consider a point A, 2, 3, and same point in 3 dimension requires 3 coordinate. Then point A becomes to 2, 3, 4. By adding z coordinate, which we consider here value 4. In 2D space, point A is here represented by the coordinates 2, 3. Where 2 is the x-coordinate and 3 is the y-coordinate. This figure shows the visualization of a point in 3-dimensional space with coordinates 2, 3, and 4. Now let's understand the concept of a line. In geometry, a line is a one-dimensional straight figure. It extends infinitely in both directions, which means it has no starting point and no ending point. A line is made up of infinitely many points. It has length, but it has no width and no thickness. That's why, even though we draw a line on the screen or on paper, mathematically it is perfectly thin. Based on shape, lines can be curved as you see here. Or it can be straight lines. In computational geometry, we mostly work with straight lines because they are easier to represent using equations and vectors. Now let's understand the difference between a line segment, and a ray. A line extends infinitely in both directions. A line segment is a part of a line that has 2 endpoints. It has a fixed length. Ray has 1 endpoint and it extends infinitely in one direction. These three concepts are extremely important because in computer geometry and CAD systems, we almost always work with line segments and rays, not infinite lines. This figure shows the three-dimensional visualization of lines. AB represents a line, CD represents a line segment, and EF represents a ray, which has one endpoint and extends toward infinity. Now let's move to the mathematical representation of a line in two-dimensional space. In 2D geometry, one of the most commonly used forms of a line is the slope-intercept form given by the equation y equals mx plus c. Here, x and y represent the coordinates of any point on the line. M is the slope of the line and c is a constant which represents the y-intercept, meaning the point where the line crosses the y-axis. Now, how do we calculate the slope m? If we know 2 points on the line, the slope is calculated using the formula m equals y2 minus y1 divided by x2 minus x1. The slope tells us how steep the line is, and it also indicates the direction of the line. Consider a line as shown. Horizontal distance is x2 minus x1 and vertical is y2 minus y1. In short, slope is vertical distance divided by horizontal distance. There is another very important form of the line equation in 2D called the point-slope form. It is written as y minus y1 equals m times x minus x1. This form is especially useful when we know 1 point on the line and the slope of the line. To conclude this, input required to create 2D line is 2 points information. Or 1 point and slope of line. Now let's understand this with a worked example. We are given 2 points P1, 2, 3 and P2, 6, 11. We need to find the equation of line. First, we calculate the slope m using the slope formula. M equals y2 minus y1 divided by x2 minus x1. Substituting the values. M equals 11 minus 3 divided by 6 minus 2. This gives us m equals 8 divided by 4, which simplifies to m equals 2. So, the slope of the line is 2. Next, we use the point-slope form of the line equation. Let's choose P1, 2, 3. Substituting the values. Y minus 3 equals 2 times x minus 2. Now, let's simplify the equation. First, expand the right side. Y minus 3 equals to x minus 4. Next, add 3 to both sides. Y equals to x minus 1. So, the equation of the line is y equals to x minus 1. This is the equation of the line passing through the points 2, 3 and 6, 11. Now let's understand the significance of the slope, denoted by m. The slope tells us the direction and orientation of a line in two-dimensional space. If the slope m is equal to 0, the line is parallel to the x-axis. This means The y-coordinate remains constant for all values of x. The line is horizontal as shown here. The slope value is 0 and in equation form, the line becomes y equals c, where c is a constant. In computational geometry, horizontal lines are important because they simplify many algorithms, such as intersection tests and scanline methods. If the slope m is infinite, this because the denominator in the slope formula, x2 minus x1, becomes 0. The line is vertical, which is parallel to y-axis. In this case, the x-coordinate remains constant. The line is parallel to the y-axis as shown here. The equation of a vertical line is written as x equals a constant. Now let's understand the condition for collinearity. 3 or more points are said to be collinear if they all lie on the same straight line. Let's take 3 points A, B and C as shown here. Points AB create one line and BC creates another line. Check their slope values. For AB it is M1. And for BC it is M2. If M1 is equal to M2, then we can conclude that given points are collinear. Now check condition for perpendicular lines. Line AB is said to be perpendicular to line CD when product of their slope values are -1. M1 into M2 is equal to -1. Here M1 and M2 are slopes for line AB and CD respectively. To conclude this, let's summarize the key ideas we discussed. First, points are collinear when they all lie on the same straight line. Second, two lines are perpendicular when the product of their slopes is equal to -1, that is, M multiplied by M equals -1. Third, two lines are parallel when they have the same slope. These simple conditions are extremely important in computational geometry because they are used in line intersection tests, geometric validations, and many real-world applications such as CAD systems, computer graphics, and simulation software. To strengthen your understanding of points and lines in two-dimensional space, here are a few practice questions based on what we've covered in this lecture. I strongly recommend solving these problems on your own before moving forward. These exercises will help you build a solid foundation for upcoming topics in computational geometry and their C++ implementations. In the next video, we'll begin applying these concepts programmatically and explore more geometric primitives. In the next video, we will take these concepts one step further into three-dimensional space. First, we'll understand the equation of a line in 3D along with its geometric significance and how it differs from the 2D case. Then, We'll move into practical implementation, where I'll show you C++ code to compute the equation of a line using 2 points in 3D space. We'll also go through multiple examples with complete solutions, so you can clearly see how mathematical formulas translate into working code. If you want to master computational geometry for interviews, CAD systems, and real-world applications, make sure you don't miss the next lecture. See you in the next video.